Yes, good afternoon, everyone. Myself is Gayatri. I'm from the Department of Mathematics. The secret of happiness is not doing what we like, but in liking what we do. Good afternoon, one and all, once again.
Madam, is it audible?
Yes, sir, it is audible.
But I'm not able to hear you, Gayatri, madam.
Yes, sir, I can hear clearly.
You can hear.
You can hear.
Hello.
Okay. Thank you, sir. So, good afternoon once again, one and all those who are present here. With the blessings of our founder, chairman, sir, late Dr. S.M. Venkatapati ji, sir, and on behalf of my Basic Science Department and EPCT organizing team, we heartily welcome our beloved young CEOs, Shri Mr. Pramod Gowda, sir, and Shri Mr. Rajiv Gowda, sir. And I also extend my warm welcome to all the dignitaries, principal, HODs of all the department, and my dear colleagues for the webinar on Pervoskites, the advanced material and their applications. I welcome you all for the webinar. Now I request Dr. Doreswamy sir to begin the webinar with an auspicious prayer song. Over to you, sir.
नमस्ते शारदे काश्मीरपुरवासिनि त्वामहं प्रार्थये नित्यं विद्याबुद्धिं च देहि मे नमस्ते शारदे देवी काश्मीरपुरवाहिनी त्वामहं प्रार्थये नित्यं विद्याबुद्धिं च देहि मे या श्रद्धा धारणा मेधा वाग्देवी विधिवल्लभा भक्तजिह्वाग्रसादान समाधि गुणगायिनी नमामि यामिनी नाथलेखालाङ्कृतकुन्तलां भवानीं भवसन्तापनिर्वापणसुधा नदीं भद्रकाले नमो नित्यं सरस्वत्यै नमो नमः वेदवेदाङ्गवेदान्तविद्यास्थानेभ्य एव च ब्रह्मस्वरूपा परमा ज्योतिरूपा सनातनी सर्वविद्यादिदेवी या तस्मै वाणै नमो नमः नमस्ते शारदे देवी काश्मीरपुरवाहिनी त्वामहं प्रार्थये नित्यं विद्याबुद्धिं च देहि
Thank you, Doreswamy sir, for having the blessings of Sharada Mate. Thank you once again. Now I request Dr. G. Maruti sir to welcome the audience. Sir, over to you, sir.
Yeah, good afternoon to all the dignitaries in the studio and my dear students. Today, Madam Srilakshmi is the professor and the head of the department in the Department of Chemistry in the Geetham University in the Bangalore campus. First of all, I would like to welcome all our management representatives, Chairperson Madam, Professor Raju sir in their absence here. I also welcome our Executive Director Shankpal sir and Principal sir in their absence here. I also welcome all the HODs and my esteemed colleagues who have joined in the online mode. I welcome today's the guest, Dr. Srilakshmi Madam, on my personal behalf and on behalf of my college and my students. Today, Madam is going to speak on Pervoskites. Just I was searching about this Pervoskites. It is noticed that it is going to be one of the potential material for making the solar cell panels. Right now we have silicon thin films which are having a conversion efficiency around 18 to max 21%. But these metals are going to have a conversion efficiency up to 66%. I think Madam is going to elaborate on this perovskite. And not only for this solar cell applications, it is used for even other applications also. Madam is going to speak on this in detail. Thank you. Now I request Shukla sir to give a brief introduction about Srilakshmi Madam, and then Madam will speak. Thank you, Anurag.
Okay. Thank you very much. And very good afternoon to all the dignitaries, to everyone present here on the studio and outside the studio. And our warm welcome to our honorable guest speaker, Dr.Ch.Srilakshmi. And of course, welcome address already expressed by Dr. Maruti sir. So I will directly proceed with the introduction of the honorable guest speaker. Dr. Ch.Srilakshmi is currently working as the head of the department and associate professor in Department of Chemistry at Geetham deemed to be University in Bangalore. She received her PhD degree in chemistry from Osmania University in 2005 and earned her postdoctoral from Technical University of Eindhoven, the Netherlands, and as research scientist at Institute of Chemical and Engineering Sciences, Singapore. She is a recipient of prestigious Inspire Faculty Award from the Department of Science and Technology, Government of India, and worked at Indian Institute of Science for 5 years. She is having a total of 19 years of research experience in the field of catalysis and materials chemistry. Her research areas of expertise also include nanomaterials, in situ spectroscopy, chemometrics, energy, and water treatment. She is the author of over 65 publications, 4 book chapters, 5 patents, and recipient of 2 DST grants and 1 UGC grant. She is acting as an editor and editorial board member to the reputed journal and reviewer to many popular journals, and appointed as member of Osmania University Board of Examiners to adjudicate the PhD thesis. She guided many MTech and BTech students for their internship and guiding 5 PhD scholars. So this is the brief introduction of Dr. Ch.Srilakshmi, and of course her expertise in the materials comes under ceramics family, that is perovskites, which are one of the most advanced materials which are being used in power conversion devices, particularly solar photovoltaics, and they have been under research for last about 15 years to increase the efficiency of solar photovoltaics and fuel cells. In fuel cells, they are used as catalysts, and I am sure that our Dr. Srilakshmi, being an expert in this field, and she has been working for over, I think, 15-20 years in these materials. And we are very fortunate to have you on board, and we are very keen to listen to your experience with these materials. And just we are expecting that we will enrich our knowledge in this field of materials through your prestigious talk today on perovskites. So I will hand over the dais for our Dr. Ch.Srilakshmi to start with your talk on perovskites. Madam, over to you.
So, thank you very much, sir, for your kind introduction. Am I audible?
Yeah,
Yes,
very much,
yes.
madam.
Yes,
Yeah.
ma'am.
So, a very good afternoon to all the dignitaries present there, and thanks for having me today here. And I'm very deeply honored and privileged, to present to you the webinar. And I want to talk about Professor Shukla here. I know him since 10 years, and I found him very, very active and intellectual, and I'm very fortunate, to know him and to work with him. And you people are lucky, he's working with you, and wherever he is there, he motivates and inspires people. And sir, once again, thanks for giving me this opportunity, and I'm ready to start the webinar. So this is the thing. Okay. Okay, so should I put in slide mode, sir? Yes. Okay, the title of my presentation today is Pervoskites, the Advanced Materials and Their Applications. So myself, Dr.Ch.Srilakshmi, working as a head of chemistry department at Geetham deemed to be University, Bangalore. Before getting into the talk, I would like to spend a few minutes to introduce you about my institute, which is Geetham. Geetham originally started in 1980 at Visakhapatnam, but Bangalore campus started in 2012 and located in a very ideal environment in Nagadinahalli on the highway and close to international Bengaluru International Airport, and it is 3.5 kilometers away from the Doddaballapur railway station. So, campus consists of four schools: Geetham School of Science, Geetham School of Management, Geetham School of Technology, and Geetham School of Humanities and Social Sciences. And campus having two academic blocks. Apart from this, we do have a library building and an academic block. So campus is provided with smart classrooms, staff rooms, well-equipped laboratories, two student hostels, and other services related to students. Okay, regarding our programs, we offer under BTech programs, we offer the following courses: computer science and engineering, computer science and business system, CSC, artificial intelligence and machine learning, cybersecurity, data science, IoT, triple E, electronics and communications engineering, mechanical engineering, and civil engineering. Under postgraduate program, we do offer MTech Data Science, MTech VLSI Design, and research program. We offer only full time in civil engineering, CSC, triple E, ECE, and mechanical engineering streams. Regarding science programs at Geetham, Department of Chemistry offers undergraduate programs: BSc Honors Chemistry, BSc Chemistry with Mathematics and Physics, and BSc Chemistry major. Under postgraduate programs, we offer MSc Chemistry with specialization in analytical and organic, and we do offer PhD in full time as well as part time. Physics department offers undergraduate programs: BSc Physics in combination with chemistry, mathematics and electronics, statistics and computer science and mathematics, and physics with mathematics and computer science. And postgraduate program MSc Physics, they also offer PhD full-time and part-time in physics. Mathematics department offers BSc Mathematics, Statistics, Computer Science, BSc Mathematics, Statistics, Data Science, and postgraduate programs in statistics, research programs both in full-time and part-time. We do have computer science program. Right now we are offering only undergraduate programs, BCA and BSc Mathematics, Statistics, and Computer Science. So apart from academics, we also actively involved in research with the funding received from DST, UGC, CSR, and AACT. So we have developed a basic research laboratories here. These are the snapshots of my laboratory. My laboratory name is Advanced Material Synthesis Research Lab, and the others. My colleague's lab is a carbohydrate research lab. Dr. Vikram Baswa, he received a TST TAIL grant and UGC grant. With that grant, he developed this research laboratory. And this is Electrochemical and Energy Systems Lab developed by Dr. Manjunath. He received two DST grants. With that, he could able to develop that energy systems lab, and the last lab is synthetic organic chemistry lab developed by Dr. Ramana with the UGC grant received. So this is about academics and research of our institution, and let's come to the talk. So today I'm going to present introduction of perovskites, structures, variations, synthesis, characterization, and synthesis of doped perovskites, supported perovskites, catalytic applications including water remediation, photoperovskites, solar cell, and conclusions. Okay, first, what is perovskite? How does gets its name? Perovskite is the name given to the oxide mineral calcium titaniate. So discovered in the, this is the perovskite here. It is discovered in the Ural Mountains of Russia by German scientist Gustav Rose. He is the Gustav Rose in 1839. Later, it is named after Russian mineralogist Lev Perovsky, who lived between 1792 to 1856. So generally, it is the name given to a family of materials that have the basic crystal structure as that of the calcium titaniate. So any material which has the structure similar to that of calcium titaniate, that will be called as a perovskite. So this is the Lev Perovsky. So the materials named after this Russian scientist. So what is this perovskite structure? It is a magical structure contains of the formula APX3. What is A, what is B, what is X? So A and B are positive metal cations. Mostly the A cations can be from alkaline and alkaline metals, and B is usually a transition metal. And the A cation is a larger cation compared to the B cation. And X is a neutral anion, usually oxygen or halide. Okay, so the diversity in property of these compounds arises from the fact that 90% of the elements from periodic table can be stable in this perovskite structure, so that we can prepare multi-component system with the formula presented here. So that is the speciality of this structure. And how does it looks like? You can see here. This is the so this is the B cation is sorry, it is okay. So the structure looks like this. B cation is present at the center of the octahedron, and oxygen ions are surrounded in a octahedral manner around the B cation. Whereas A cation, it can be alkali or alkali metal, sitting in a 12-fold coordination. So formed in the middle of the cube of the 8 octahedrons formed by BO6 octahedron. Okay, so there are variations, several variations. So the ideal structure is the cubic structure. However, some of the perovskites displayed simple distortions from ideal structure. So what are the reasons for the distortions? Distortions is mainly because of rotation or tilting of VO, VO6 octahedra or BX6 octahedra, or a distortion of this octahedra, or distortion of A and B cation polyhedra. Okay. Shukla sir? Shukla sir, can you hear me?
Hearing, madam. Continue.
So is there any thing pointer so that I can point something? Yeah.
No, on the slide, if you right click, you will get the list, and in that you can have the pointer, and that pointer you
Okay.
can activate. You will get a red pointer.
On the slide.
On the slide, you take the cursor, right click,
Wait.
and somewhere the lower part you will get the pointer, optical pointer or something.
It is
Is it?
not showing here. Maybe it is not showing here. Okay, that's okay, because I just want to I want to show with the laser pointer. That's fine. Okay, so what are the reasons behind the distortions? Distortions are mainly due to size differences between A cations and B cations. So these distortions play a significant role in the properties of these materials, and the factor that is called tolerance factor links the difference in structure to the difference in cation size to the structure of the perovskites. Okay, so this is nothing but T is equal to ratio of ionic radii of A cation and oxide anion by ionic radii of B cation and oxide ion. So these distortions can be controlled, and if you can control these distortion specific properties of these materials can be achieved. And the tolerance factor should be in between zero point 0.9 to 1 if you want to really prepare a cubic structure. And if it is greater than 1, it forms hexagonal or tetragonal crystal structure, and so on. If it is 0.74 to zero point 0.9, orthorhombohedral and monogenic structures will be formed. So you can always target. Suppose if you think that a tetragonal structure is really suitable for your application, so based on this one, you can choose the elements and fit in here and calculate accordingly. If that falls like greater than 1, it really gives that cubic. It really gives that crystal structure. So classifications of perovskites. Basically, there are two types: inorganic oxide perovskites and halide perovskites. Inorganic again divided into intrinsic perovskites and doped perovskites. So here, doped perovskites are only there, but I invented a new perovskite called supported perovskite, which I am going to talk in the lecture, and halide perovskites, which is alkali halide perovskites and organometal halide perovskites. So these are very important materials. They are now given wide importance because of their applications in photovoltaics. So, apart from photovoltaics, what are the other applications of these materials? So, again, applications depends on organic and inorganic perovskites. Inorganic perovskite nanomaterials are used as electrode materials in electrochemical sensing of alcohols, gases, glucose, etc. And they used as anode or cathode materials in fuel cells, batteries, and they used as catalysts mainly in water splitting and photocatalytic degradation of many organics. And organic metal halide perovskites are mainly used as a perovskite solar cells, lasers, and thermoelectrics. So this telling that they are not only observing the light but also emitting light. That's why they can be used as lasers. Among all these applications, so catalysis part, particularly liquid phase heterogeneous catalysis part, is less explored. Not many applications are there. So when I got DST grant, I thought of why can't I explore these materials for catalytic applications, so particularly for liquid phase, as there are no applications on this area. So I thought of, so let's have a basics. Catalysis is the process of increasing the rate of a chemical reaction by providing an alternate pathway. So in perovskites, the usually B sites are the active sites where most of the reactions takes place, whereas the A sites just provides support to the perovskite structures. It does not have any catalytic role. So B is the active site on which chemical reactions takes place. So due to the diverse compositions available, perovskites are being mostly researched for photocatalysis and methanol production. So, what are the challenges in order to use these materials for mainly liquid phase heterogeneous catalysis? The one thing is, the catalytic properties mainly depends on the surface area of the materials. So, in order to increase the surface area of the material should be porous. So one of the challenging is synthesis of highly porous perovskite materials and application of these materials for the liquid phase heterogeneous catalysis reactions and improving the reactivity of these materials for these reactions. So these are the challenges I faced during my research on these materials, mainly for applications in the liquid phase heterogeneous catalysis. So I devised new methods for the synthesis of these materials under low temperature, and also modified the existing high temperature synthesis methods. So what are the methods I developed? Or microwave hydrothermal synthesis and solution combustion. You might wonder that solution combustion method always exists, but I modified the existing solution combustion method with a mixture of fuels approach. Let's see. So before getting into the details, we need to understand about microwave heating and conventional heating. What is microwave heating? Microwave heats interacts with the all contents of the reaction mixture. There is no thermal conductivity difference. Means energy transfer is uniform and efficient throughout the sample. Okay, so whereas in the conductive heating, it rely on thermal conductivity. First, from vessel to the source, energy transferred or heat transferred from source to the vessel, then vessel to the solution. So you know it is a very slow or not efficient way of heat transfer. Okay, there are differing thermal conductivities, so that's the reason you can always see the formation of bigger particles in a conventional way of heating, whereas in microwave particle size is very less, because it causes molecular agitation and it causes friction among the molecules. So particle size of the materials prepared by microwave heating is very small compared to the conductive heating. So that is the basic underlying principle. And what are the advantages of microwave synthesis? We can achieve fast crystallization, and it is a clean technology. Why is a clean technology? Mostly water and ionic liquids are used as solvents in synthesizing the materials, and not much power is required. That's the reason it is a cost efficient and energy efficient, and moreover, it is economical. So, before going into the modified or which I developed in solution combustion synthesis, let's see the conventional solution combustion synthesis. So, it consists of three steps. One is formation of combustion mixture. Second is formation of gel, and combustion of gel. So initially, to form the combustion mixture, we need to dissolve the metal precursors, which are acts as oxidants also, and fuel in required amount of water, and this should be treated at 80 degrees C. So due to dehydration, it forms a gel-like structure, and this gel-like structure should be kept in the preheated furnace or oven at 400 degrees C. Then it causes a fire and produces the powder, black powder. So here what is important to be noted is the nature of fuel. The amount of fuel definitely influence the material properties of the final compound, and also fuel to metal ratio also it influences. So keeping this in mind, I come up with the new method where instead of individual fuel, I have taken a combination of mixture of fuels, and and I mix them along with the metal precursors, and I place them on the preheated hot plate at 180 degrees. Then what happens? It boils and concentrates, and finally foams and catches fire and gives the a precursor material which was calcined at the desired temperature. So instead of 400 degrees, it reduced to 180 degrees, and the evolution of CO2 N2 are quite minimum compared to the uh, conventional solution combustion synthesis. So this is the property. So here only single fuel taken in the modified approach. we have taken a combination of mixture of fuels and also reduced the combustion temperature from 400 to 180 degrees. So what are the advantages of solution combustion? It is quite rapid and reproducible, and it can be scalable, simple, versatile, different types of materials. Not only this one, anything you can prepare using solution combustion synthesis. Efficient and is okay, eco-friendly. Okay, so before getting into the details of the work that I have done, I want to just give you a brief introduction of the characterization techniques I use for material characterization and also the information one can obtain from each and every technique. Suppose if you use a powder X-ray diffraction, you can identify the phase and you can also calculate the crystal size determination and read-wheel refinement. It is a theoretical method from which we can evaluate the crystal structure and also lattice parameters evaluation. Based on that, we can predict the crystal structure of the perovskites. So this is a theoretical method which uses the data that is generated from the X-ray diffraction to give it gives information about the crystal structure and lattice parameters. And infrared spectroscopy. So I use infrared spectroscopy to identify the functional groups and also to determine the type of acid sites present in the sample. And TZTTA, thermogravimetric analysis, gives information about the stability and also the phase transition temperature determinant can be obtained. So N2 physics option by BET method is mainly to obtain surface area and the pore volume of the materials, and SEM, which is scanning electron microscopy, to know about morphology and topology of the sample. TEM also the same purpose, but here we can also determine the particle size of our sample. So TEM EDAX. So most of the TEM equipment is EDAX is energy dispersive X-ray spectrometer. If we have this add-on accessory, it can give information about the elements that are present in the sample. And finally, X-ray photoelectron spectroscopy gives the same whatever the information we get here, the same information along with that. So oxidation state or chemical state of the elements that the sample contains. So this gives a brief idea about the characterization techniques I use for my studies and the information obtained. So let's get into the work. So this is the microwave synthesis of chromium doped barium titaniate catalyst. So actually, when I look into the literature, what is the procedure I should follow, like that? So zero reports came up. So I thought, why this is a chromium doped? What is happening? So I took this as like it is interesting to prepare this material, and finding applications for this one. So what are the raw materials? Titanium chloride, barium chloride, and chromium nitrate are used as precursors for the preparation of chromium doped barium titaniate. So here you can't really use whatever the material you want in microwave synthesis, because that those materials or raw materials should be good microwave absorbents. Then only required phase will be obtained. So here you see at least along here chromium chloride I cannot use because it is not available. So I have taken chromium nitrate and mixed with barium chloride. This is a chloride precursors are good microwave absorbents. So you can use all chloride precursors except one or two, so that heat will be transmitted nicely in the mixture. So all these ingredients are mixed in this ratio mentioned here. First, initially, titanium chloride is dissolved in water at 0 degrees. Later, barium chloride, chromium nitrate, and KOH separately dissolved in deionized water, mixed to the titanium chloride solution, and the resulting mixture stayed 30 minutes at room temperature, then transferred to the autoclave and autoclave to the microwave and irradiated at 180 degrees for 30 minutes. Okay, so to optimize these conditions, it took for me 3 months. Took for me 3 months. Why? You may be, this is silly. Why it took 2 months? Because you see, this kind of molar ratio develop. So if I take less water or if I vary this 10 or 15, the phase is not coming. Something else is coming. Different types of compounds are coming. And also, even 1 degree is also matters in microwave. So finally, uh, 180 degrees, 30 minutes is the optimizer microwave reaction conditions to synthesize a pure form of perovskites. And synthesis by high temperature oxalate method. This is the procedure. We use barium nitrate, chromium nitrate as metal precursors, and a titanium isopropoxide as a titanium precursor, and I use oxalic acid as a complexing or reducing agent and mix them together in isopropanol and water mixture, and homogeneous solution obtained at when stirring at 60 degrees for 1 hour. After that, evaporation of the solution at 100 degrees C. So the obtained oxalate precursors are dried at 120 degrees, then calcined at 900 degrees to obtain the perovskite phase. So this is the molar ratio of these ingredients maintained to prepare the chromium to barium titanium catalyst using oxalate method. And you can see, so these are the powder X-ray patterns of the chromium doped barium titanium catalyst. So according to our table, what we can identify, one is the phase, another is crystallite size determination. So the phase, let's see what phase is present in conventional oxalate synthesized the samples. All these samples show tetragonal barium titaniate phase. So in all the samples, along with the extra phases such as chromium oxide, barium carbonate, titanium oxide, etc. So these are all the secondary phases as impurities observed in particularly chromium doped barium titaniate catalyst. So these are absent in pure barium titaniate sample. Whereas in microwave synthesized samples, you can see, this microwave synthesizer samples exhibits cubic barium titaniate phase, whereas in CO it is a tetragonal phase. How we can differentiate between tetragonal and cubic? So there is a this is the peak at 2 theta 45 degrees. You can see a split is observed. So it is, corresponds to 002 and 200 plane here, whereas same place at 2 theta 45, this split is absent in microwave synthesizer compounds. That's how we differentiate the tetragonal and the cubic phases of barium titaniate present in CO and microwave synthesizer compounds. So now you can see what is the difference between these two samples here. This one in CO synthesizer samples, you can see the presence of secondary phases, whereas these are absent here. It means that one can synthesize the pure compounds by using microwave hydrothermal synthesis method. Okay. So these results are published in Inorganic Chemistry in 2016. And these are the read-will refinement of XRD. So how do we know that whatever we have confirmed via XRD, is it really true, or can we confirm this one via theoretical analysis? Yes, we can. We can do that one. That method is called read-will refinement. So described by Hugo read-will, through which we can always calculate the theoretical XRD pattern which should match to our experimental pattern. So here the results you can see here. So Y is the red is observed and the black is the calculated. The difference between the calculated and the experimental spectrum should be 0. Then only it reveals the nice speed. And along with this one, what are the parameters, the crystal structure determination, and also lattice parameters we can get. For example, in the next slide I have shown here, whatever the parameters we have got from the readable refinement of the microwave synthesized the samples. Here it further confirms refinement results further confirms that the cubic phase of barium titaniate is present in the microwave synthesized samples, and the lattice parameters you can see lattice parameters increased with increase in the chromium content in the sample, which is obvious because the ionic radii of chromium is a little slightly higher than the titanium. That's the reason there is you can see the cell volume also increases with increasing chromium content, and also lattice parameters also increases. So with this information here, we can model a structure. We can predict the structure using another program called Vesta. So these are the structures calculated or predicted using that program. In that it gives like this is the unit cell where barium is present at the 8 corners of the cube, titanium at the body center, and oxygen at the face center. Okay, so this is also regarded as the barium means 12-fold coordination and titanium means 6-fold coordination. So we have further conformed theoretically through read-field refinement analysis that synthesized materials exhibit tetragonal barium titaniate phase, whereas microwave synthesized samples exhibit cubic barium titaniate phase. Okay, so the morphology and the particle size determination was conducted by using a transmission electron microscopy. So, for example, I didn't give here all the things because it will take time. So, just for a sample, I have given here 2.5% chromium doped barium titaniate sample. You can see here the particles are very large and are lightly agglomerated, whereas the microwave synthesizer sample shows smaller particles and they are nicely distributed over the sample. So particle size determination, there is a tool in the 10 thing scale tool, then it can give using that tool you can always calculate the particle size. So conventional synthesized barium titaniate is 30.8 and the crystallite, the particle size of chromium samples increased with increasing chromium content, whereas microwave, you can see here 30.8 in microwave synthesized sample, it is just 20.7 particle size. However, the particle size increased with increase in the chromium content of the sample. But if you see almost 10 nanometers difference, it is a huge. So this particle size is within 0 to 100 nanometers. So we can declare this as a nanomaterial. So, but not the bulk material. And the particle size of the microwave synthesizer material is very small compared to the conventionally synthesized material. Let's see whether it has a effect on catalytic activity or not. So we also measure the high resolution images of 2.5 chromium doped. This thing you can see, this is the high resolution temp image. You can see the clear lattice fringes, and we have calculated the d spacing between these two crystal planes, and it comes to 0.283 nanometer, which is 101 plane of CO synthesizer material. And this one here, we calculated 0.28 nanometers, which belongs to 110 plane of 2.5% chromium doped in microwave synthesized materials. And the IDAX analysis reveals the presence of barium, titanium, oxygen, and chromium present in the samples. So here you can see clearly because very small images. If we zoom in, we can see clear. So we further confirm that so chromium is doped in place of titanium. So what are the other physiochemical properties we can determine? So BET surface area. So TEM analysis give an idea that particle size of microwave synthesized materials are small. So what are the results, what the BET surface area results does? You can see here. So this is 1 to 4, this is barium titaniate, and 0.5, 2.5 and 5% chromium doped CO synthesized, which is conventional oxide. So BET surface area of barium titaniate synthesized by CO method is 8.9, whereas you can see here the same barium titaniate without chromium is 71.4. Almost is 10 times, and whereas 2.5 chromium 20.8. So this surface area increased until zero point 0.5 until zero point 0.5. After that, it is gone to decreasing trend. Same with the case pore volume. You can see 2.54 into 10 to the power of 3, and here 3.55 into 10 to the power 10 times. So surface area increased, pore volume increased. Let's see about the Lewis acidity. So this is 327 and this is 329. So acidity also increased. Means these results indicate that if you use a perfect low temperature method, so you can always synthesize the material with good physical and chemical properties. So how do I confirm that the acid sites are Lewis acid sites but not the Bronsted acid sites? So we have done the pyridine adsorption studies using IR spectroscopy. In the IR spectra of the pyridine adsorption samples, we observed two bands at 1431 and 1634 belongs to pyridine chemisorption on Lewis acid sites. So if it comes out and Bronsted acid sets, it should give peak at around 1550, which is absent here. So it tells that only these sites are present in the barium titaniate and chromium doped barium titaniate sample, and Bronsted acid sites are absent. So XPS. So what we have learned from the table, why should we use XPS? One is elemental composition, another is a chemical state of the sample. So this is the survey spectrum. So this is the survey why it is. So this is the survey spectrum where you can see the presence of all the elements that the sample is composed of. For example, barium carbon is not there. So where this carbon comes from? Maybe it is from the atmosphere, it picks. So apart from that, barium and titanium, chromium, and oxygen are there. So now we can see, I just shown here the chromium. I want to know what is the oxidation state of chromium in the chromium doped samples. So normally we have observed two broad bands here. One is 577 and 589 something here, and these are very broad. So we use Gaussian fitting procedure to fit, and once we fit the thing, this broadband consists of three small bands, and these small bands correspond to chromium 3 and chromium 6. So my sample is composed of mixed oxidation states of chromium, but not the single oxidation state. As we have seen before, you see this is the speciality of the perovskite structure. It is stable the elements in different oxidation states in perovskite structure. So after we characterized our samples, we have tested these materials for the catalytic reduction of nitroaromatics into amines. So we have transformed nitrobenzene into aniline by using hydrogen hydrate, hydrogen hydrate as the reducing agent, and catalyst is all the catalyst we have synthesized and KOHA, and the solvent is the isopropanol solvent. So before proceed with this reaction, we need to optimize the reaction conditions. Means how we can do that one? You need to see the influence of temperature, solvent, and catalyst. Okay, so with this optimized reaction conditions, we understood that a temperature of 80 degrees is really suitable to obtain 100% yield, and 2-propanol is the best solvent, and 80 mg is the optimum catalyst loading to achieve good yields. So we kept this reaction condition constants, and we have run the catalytic reduction over all the catalysts synthesized via CO and microwave catalyst. So first four here is a CO means conventional oxalate method synthesizer catalyst. First, we can see that one. So, barium titaniate required 6 hours, and it is less active. Given only in 6 hours time, given only 80% conversion with 96% selectivity. So, whereas the chromium samples, the activity is improved until 2.5, and after that remains constant. The same thing, 100% yield is obtained on zero point 0.5 chromium. So whereas if you take this microwave synthesizer samples, BTO5 is the barium titaniate synthesized using microwave. So the 100% conversion and selectivity we can see. So after that conversion remains constant, and the selectivity is goes down because of the side reactions here. Sometimes if we have a very active material, highly porous, and if we are incorporating something into that one, obviously the catalytic activity will go down. So these results indicate that no matter means this promoters here chromium. What is the role of chromium in this metal? So it is very obvious in conventionally synthesizer catalyst, because with increase in chromium content in the catalyst, conversion increased. But here I don't see any improvement, because here you can see here conversion remains constant, and selectivity goes down because it is blocking the active sites here. Okay, only thing, the role of chromium in microwave synthesis thing, it facilitates the reaction in short time. That is only the thing. So it facilitates the reaction in short time here also, but here in terms of activity it clearly improves the conversion as well as the selectivity. But with microwave synthesized, everything is constant, only facilitates the reaction at short time. So these are the conditions we have used here. Reaction is conducted in a round bottom flask by dispersing 80 mg catalyst in a nitrobenzene, KOH, and hydrogen hydrate mixture, and 2 propanol is used as a solvent and refluxed 2 to 6 hours at 80 degrees C. All the products here are analyzed using GC mass. So what about the substituted nitrobenzene? Whether in order to see the scope and applicability of the protocol we developed, whether really applicable for the substituted compounds or not. Yes, we have seen, and you can see the good yields here. In this case, 1-chloro-2 for nitrobenzene. Only one of the nitrobenzene get reduced, and the remaining you can see the para compounds. So para substituted compounds or substrates gave good yields compared to the ortho substituted compounds. But we have got good yields of the desired products for the substituted nitrobenzene compounds also. Recyclability. So we have tried whether we can recycle this catalyst. For that we have chosen the 2.5 chromium doped CO synthesizer and microwave synthesizer catalyst, and it reveals that we can use without loss in activity until 4 cycles. Okay, until 4 cycles here you can see here. Anyhow, in a BTO7 means this is the 2.5 thing, because as we have seen there is no role of chromium dopant in microwave synthesizer, but you can see there is no loss in activity. So these recyclability tests indicate that we can use the same catalyst uh, 4 times. So how do we do what is the procedure for recyclability? So after the reaction completed, we We centrifuge the reaction contents, separate the solid catalyst, wash with water or ethanol, and dried it in oven for overnight, and we can reuse it. So this is the procedure we should follow after each and every run. So that is about the case one study. So if you have any doubts, I can take, or otherwise I can proceed with the next thing. Okay, so this is what, as I discussed before, modified solution combustion synthesis. So instead of single fuel, I have taken combination of mixture of fuels. So what are the fuels I have used for the synthesis of strontium ferrite? So citric acid, oxalic acid, and glycine. And the combinations are citric acid, glycine, oxalic acid, glycine, and a combination of all these three fuels. And again, in the XRD, except in the second sample, which was synthesized by using just individual oxalic acid, all the samples showed a impure phase here, which is some here not seen S4 Fe2 something that, and IR confirms that there are FeO stretchings, and this is a broad bond contains the shoulder at 545. So that indicates the strontium ferrite is a defective structure. Here 3 minus delta, it is not 3. So it is a defective perovskite, not the complete perovskite. And physiochemical properties determination, again you can see these first three of the samples prepared using individual fuels, and 4 to 6 are combination of fuels. You can see surface area improved, pore volume improved, acid strength. When you come to acid strength, it goes down. So acid strength of this material goes down when we use the combination of the fuels. What about the crystallite size? So compared to the crystallite size of the individual fuel samples, the crystallite size of the mixture samples are less, and the crystallite size also means particle size also calculated using the SEM, and it is in between 210 to 302. So this is okay, that is all about. So this is the equation we use for the calculation of crystallite size using XRD, called Scherer-Von equation, which is this is the wavelength of the X-ray, and these two B's are the full width of maximum of the reference and the sample compounds. And these are the SEM images, as you can see. So because of this magnetic nature, this compound shows a highly dense agglomerated spherical particles. But at last, the sample prepared using combinations of three fuels, all three fuels, the morphology is changed to plate-like structure, star plate like this. This was further confirmed by TEM analysis. Okay, so these are all the same images, whereas we have confirmed the change in morphology by analyzing the sample using transmission electron microscopy. So this confirms that the last sample prepared by using all three fuels has a different morphology, which is a hexagonal plate-like morphology. And TZDTA profiles how this compound transforms. As I showed you, the one is stability, and the phase transformation temperature we can identify from the thermodynamic analysis. So this shows that so there are four major weight loss. First is the loss of water, and second endothermic peak is decomposition of organics. Third is strontium nitrate interacting with the CO2 and converts into strontium carbonate. So this is the peak. This is very important at around 850. So strontium decomposition of strontium carbonate into strontium oxide, and further interaction with the iron oxide in the presence of O2 gives rise to the formation of the desired compound, which is a defective strontium ferrite the structure. So from these studies, what we have known, at which temperature we should calcine this sample. So when we calcine this sample above 850, definitely we will be getting this phase. That information we'll get. So once we calcine the catalyst at 850 or 900 degrees, we applied this material for the catalytic reduction of nitrobenzene. Yes, this is the beauty you can see. Previously, in the previous case study, we have used hydrogen hydrate as our reducing agent. Now, isopropanol itself we have used as the reducing agent, and instead of aniline we got azoxybenzene. I was so depressed. We have targeted for aniline and azoxybenzene, so whether these results are trash or what. Then I asked my student to look into the importance of azoxybenzene, and to my surprise he told that, ma'am, actually we are lucky, we don't need to be disappointed because there are no heterogeneous catalytic routes for the synthesis of azoxybenzene, and we are the first people to develop this one. When I submit this paper to the inorganic chemistry, just within 10 days time, without any revision, they got accepted this one, saying that this is the new method you have developed. So here one is synthesis is new, and also new way to synthesize the azoxybenzene. You can see these three are the samples prepared using individual fears, and from 5 to 7 the mixture of fears. So the conversion goes up, and whereas the selectivity also goes up. So there is no correlation between conversion and acidity, because here acidity is more in the samples synthesized using individual fears, but not in the samples synthesized using combination of fears. So here there is something, this acidity related to the selectivity. It means that in order to form azoxybenzene selectivity, redox nature of the catalyst is essential. Redox nature of the catalyst means it should not be more acidic, less, it should be moderate acidic. So that increases the azoxybenzene. That's the reason instead of aniline we got, because here what we observed is in these samples aniline is more. We didn't give here, aniline formation is more. So in order to form selectively azoxybenzene, definitely we need to have the moderate acidic strength, but not the high acidic strength. So we have proposed, we come up with the new reaction pathway. Then reviewer asked, so can you propose the reaction pathway? Yes, sir. We came up like this. You see, when you use hydrogen hydrate, the reaction goes like this. Okay, so nitrobenzene converted into nitroso, hydroxylamine into amine. But here what is happening, since we are using 2-propanol as both the solvent and the reducing agent, first it should be converted into acetone, then H2. Even N2H4, which is hydrogen hydrate, should be converted into N2 and H2. So N2 is something inert, but here 2-propanol is converting into acetone and H2. This H2 will be utilized to form azoxybenzene. So here what is happening, this nitrosobenzene and hydroxylamine undergoes coupling reaction and forms selectively azoxybenzene. In order to convert this one into aniline, you need to further hydrogenate this one to ethobenzene, then hydrobenzene, hydroethobenzene, then it converts into the aniline. So since we came to know that one, this is the compound where used in the liquid crystal systems, and also as a dye, importance of this compound is huge. We thought of just publishing like this. So this is the not tentative, this is the mechanism, proposed mechanism by us. Nowhere else you can find this thing. Okay, so that is about the second case study. And we thought of, why don't we apply this material for something else? So I thought of, using the material, the pure material synthesized by using the individual fuel, which is oxalic acid, where the secondary phase is absent. We have taken that material and we have tested this one for the photocatalytic reduction of nitrobenzene. Since this material shown activity for the catalytic reduction, why can't we just use like a tip off? Why can't I use the same material for decomposition of the same. So this is the photocatalytic setup I have used for photocatalytic degradation. It is a wooden case fitted with UV light, and this is the glass reactor. Both these things, which is not shown here, encased in a quartz tube in order to circulate water through them to avoid any thermal decompositions. So all the photocatalytic experiments are conducted at the room temperature. So prior to UV irradiation of the sample, what we have done is we have stirred the reaction mixture at room temperature in dark for 30 minutes in order to attain adsorption desorption equilibrium of between the catalyst and the reactants. And after that, for kinetic studies, what we have done is 5 ml of the reaction mixture taken at regular intervals after UV radiation and analyzing them with UV visible spectrometer, and the unknown concentration was obtained by using the calibration curve of the UV visible data. So these are the profiles, you see. So we have conducted in two ways: degradation of nitrobenzene by using UV and catalyst, that is strontium ferrite, and also another way UVFO and this one H2O2 in the presence of oxidant and in the absence of oxidant. Just UV and the catalyst. Here is something is not shown here. So these are the profiles we have. These are the profiles we have created from the data obtained by using UV visible spectroscopy. So you can see here, this is the y-axis is the concentration of nitrobenzene, versus time. Like that, for various concentrations of benzene, we have plotted. So these are the experiments conducted with the catalyst under UV radiation. 50, 50, 100, 200, and 300. You can see almost this is at low concentrations of nitrobenzene. Degradation is 99%. But when you come to high and it degrade in less time, whereas at high concentrations it took long time to degrade to 97. So here 99, 99, 99, but here 96 percentage. Whereas here you can see, I just thought that why I want to know whether it is the catalyst is really degrading the degrading the sample. It is something
Again, it got disconnected. From there, it is disconnected because I'm not seeing the other side. I'm seeing only my camera.
It is connected, ma'am.
Yeah, sorry for the inconvenience caused because it never happened today. I think some problem. Okay, so where is the presentation? I can't see.
You share the slides, ma'am.
Okay, again I should share. Okay.
Huh.
Yes, it came.
Huh.
Yes, yes, yes.
Again.
My
You go
order.
for the
This is
slide.
not. Yes, 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 yes. I'm going.
It's not connected, ma'am.
Yes, here I am. So as you can see, with increase in the concentration of H2O2 in the reaction mixture, the degradation is decreasing. Okay, the degradation should be increased, so it is decreasing. It means something is happening, something is blocking it. Then later we try to find out. So what exactly is the reason? You know. Uh, why the degradation is less when we use H2O2 with UV and SFO, why it is degradation is more with just UV and SFO catalyst. So what is happening? We try to find out, and so we have modeled the data, and it fits nicely into the first order. First, it follows the first order kinetics, and we have calculated the rate constants using the slope of these, curves here, and we have plotted here. You can see from low to high concentration without using H2O2, it just degraded low time, and from 99 to 96, and the rate constant is also good compared to the uh, degradation using H2O2 for nitrobenzene degradation. So with 1:1, it is a rate constant is a 0.346. It goes down when I increase the molar ratio of H2O to 0.29, and it further goes down like this. Okay, so these results implies that the catalyst is doing the best job. We don't need to use any H2O2. So reviewer asked, so we submitted like that. We don't know what is the reason. Let's submit. Then my student was telling that, ma'am, our paper will definitely get rejected. By the way, these results are published in industrial engineering and chemical research, which is a very good paper. Let me discuss first this one. So, what is the reason? They ask only one thing. What is the reason? H2O2 is a good oxidizing. It's the result is supposed to be good compared to the just catalyst and the UV radiation. So no, we don't know, and they gave, if you want, you can reconduct the experiments and come up with some explanation. So 3 months they give time. So we were thinking, and nothing is happening. So I asked him one day, you repeat one of the experiment, and collect the user catalyst and give it to IR and XRT. Then, interestingly, to our surprise, we found this results. So, strontium carbonate is forming in the H2O2 based catalyst. Okay, so we further confirm this is the standard IR pattern of strontium carbonate sample IR, and this is the sample, just UV and SFO sample without H2O2, in the reaction mixture. You can see this 571, as we have seen before. This is the nothing is there, just 571 is the FeO stretch. There are no bands here. Okay, strontium carbonate. So, what is the mechanism where this strontium carbonate comes from? So, what should I do? Then, what I propose like this means the reason is what is happening in the presence of H2O2? Excess of hydroxyl groups are there. Excess of hydroxyl groups are there. So these excess hydroxyl groups interacting with the dissolved CO2 in the solution and forming bicarbonate. Bicarbonate is converting into carbonate, and this carbonate that is formed get reabsorbed on the catalyst and blocking the active sets. That's the reason why the degradation is low with the H2O2 of the catalyst. Okay, so what is happening in the UV? Then we have proposed the reaction mechanism based on the props we detected using HPLC analysis. So before that, let's see what happens when UV light shines on the strontium ferrite. It produces electrons and holes. Electrons goes to conduction band where it interacts with O2 and forms OH radicals, whereas holes interact with the H2O and form so. These OH radicals that are formed will oxidize and reduce the nitrobenzene into CO2 and O2. So here nitrobenzene is converting into ultimately CO2 and O2. That CO2 is what is happening. It is interacting with the hydroxyls and forming bicarbonate, and bicarbonate converting into carbonate, and carbonate is getting reabsorbed on the catalyst surface. That's why degradation is very low on the over the catalyst where we have used H2O2 as the oxidizing agent. So, and we proposed this reaction mechanism. Nitrobenzene upon interaction with OH radicals first converts into hydroquinone, then benzoquinone, then malic acid, oxalic acid, and finally with the CO2 and water. So this is one of the beautiful study on this strontium ferrite, and we have compared our photocatalytic results with the titanium-based catalyst. You can see we are using from 50 to 200 and 300 very high concentrations, and we use 125 watts UV light and the 100% degradation in 6 hours. Whereas a titanium-based catalyst very low concentrations, but they have used high power UV, but none of the catalyst showed here 100% compared to the my catalyst system. Okay, this is about a comparison with the reported titanium based catalyst. We all know that titanium is the best catalyst for photocatalysis because of the band gap. And by the way, the band gap of this material we have calculated by using the UV absorption spectrum is a 3.75 electron volt, and which is 340 nanometers. So it falls in the UV rays. So we declare this material as UV active. That's the reason we use UV degradation of nitrobenzene. Okay, so in another study, so now I want to see whether we can prepare a material where it can do the multitasking. Means the same material we can apply for different reactions as we have done with the strontium ferrite. Then I prepared strontium titaniate, both conventionally CO method and a microwave method, and applied for novel condensation, transfer hydrogenation, and amination. And so all these props are the useful raw materials, for the synthesis of important pharmaceuticals, agrochemicals, pesticides, etc. So this is a kind of a first study where we have shown the single perovskite different applications. So this is published in ACS Omega, and as you can see, this is XRD of conventionally synthesized strontium titaniate by using oxalate method, and this is the microwave method. You can see all the time, you can see the pure compounds we can get by using microwave synthesis method, and both the compounds exhibit cubic strontium titaniate phase. And here TEM analysis. Here, you can see this is a large cubic nanoparticles are appeared or observed in conventional synthesized strontium titaniate, where you can see the beautiful, nicely porous small particles are uniformly dispersed through the sample. And you can the acid strength and total acidity. So total acidity is all about whether the Lewis acids or Bronsted acids. Acid strength is something like that, whether the acids, Lewis acids are strong enough, or they're really acidic, or moderate acidic, or weakly acidic. That one, two types of acid measurements we have conducted. One is to find out the acid strength. We have used N-butylamine titration, and we have used the electrodes to measure the electrode potential. If the electrode potential, initial electrode potential is greater than 100, then that material contains a very strong acid side. So both the materials shown above 100 millivolts. That's why they both are strong, but compared to the conventional catalyst, the microwave synthesizer catalyst is the strongest acid sites are present in that one. The acidity both contains Lewis acids, but the acidity, total acidity is more in microwave synthesizer catalyst compared to the conventional. So here BET surface area, sir, could you please reduce this one, label this one, because this is very important. This so here BT surface of 5.11. Here something. Shukla sir. So you please remove this name tag here. You can see the. Hello. Okay, the particle size here. Shukla sir, can you hear me? Hello. Hello. Shukla
Yes,
sir.
madam, I am hearing. Yes.
So can you remove this name tag once? I want to show interesting because
Gayatri madam, can you remove the caption from the bottom because it is holding the table? Yeah.
yes, this is very interesting. That's the reason you can see the surface area is just 5 for STO prepared by conventional method, and whereas this one is 69, and you can see the pore volume was almost 10 times, and the pore diameter both containing mesoporous, because the pores in between 2 nanometer to 50 nanometer are called as mesoporous materials, and the particle size you can see this is 102 nanometer, whereas this one 21.4, and the crystallite size is also less. So this is the beauty of this microwave synthesis method. And as you see here, these are the reactions we have conducted. These are what is no vinegar condensation, where we will be taking benzaldehyde interacting with the active methylene compounds, which is ethyl cyanoacetate, for example, if you take, and you will be getting alpha, beta, unsaturated compounds. And you can see here the activity for this reaction is so both showed good activity, whereas the conventional catalysts, given the 100% conversion in 35 minutes, in whereas microwave material just given in 15 minutes. Just like others, the hydrogenation, conversion of nitrobenzene to aniline, here also you can see in 1 hour the reaction got completed. In all the reactions, what we understood is the amination. Amination is something like reaction between aldehydes and amines gives Schiff's basis. Okay, so all these the products are the useful raw materials for the synthesis of agrochemicals, pesticides, pharmaceuticals, etc. So from these results we can say that microwave synthesizer material is excellent for any type of reaction you can explore. We have also tried with the the substrates, which I am not going into detail. And another thing is we have I heard this is what the new material I came up with. I used strontium titaniate as a support, and I dispersed the vanadium active component on it. This is something nobody has tried before. And as you can see, this is the STO, strontium titaniate, where cubic phase is observed. So with the incorporation of vanadium, until 1 weight percentage, you can't really see the vanadium oxide. Okay, it means that at low concentration, and vanadium is nicely dispersed in the pores of the strontium titaniate. So at high concentrations only it will be seen. So presence of vanadium oxide is seen very clearly in the IR spectra also. The band at 891 corresponds to vivo stretching vibration. So these are the TEM and DDAX again. You can see the morphology, the samples contain in spherical particles and the cubic nanoparticles, and the morphology is changing from spherical to the plate-like structures. Morphology change initiated in 1 weight% vanadium on strontium titaniate, and it is completely 80% change to plate-like structures here. The again incorporation of vanadium is confirmed through TEM and EDAX analysis. So what is this? Whether it has an effect? And again, these are the physiochemical properties you can see. So crystallite size is increasing here, because this increase in crystallite size is in good agreement with the increase in the particle size. Why this is increasing? Because the morphology is changing from spherical to plate-like structures, and the surface area of the pure strontium titaniate is 5, and it is a little low in 0.5. What does it mean by at low concentration the vanadium is nicely sitting in the pores of the strontium titaniate? With increase in the concentration of vanadium on the surface of strontium titaniate, what is happening? The contribution from the vanadium is coming. Contribution from the vanadium oxide leads to increase in the surface area of the samples. So pore volume again. Pore volume, you can see pore volume is increasing. That is, the pores are filled with the vanadium oxide. So Lewis acidity, you can see Lewis acidity is increasing until 1 weight%. After that it goes down. This is due to change in morphology of the samples. So again, you can see the Lewis acidity is confirmed. Only Lewis acids are present in the sample, but not Bronsted acid sets, even after incorporation of vanadium on the surface of the strontium strontium titaniate. These are the, so we have applied this catalyst for the catalytic oxidation of benzyl alcohol to benzaldehyde. You can see here we have conversion and variation of activity with the variation in vanadium content of the samples. You can see STO is least active but moderate selective, whereas the vanadium catalyst, the conversion as well as the selectivity improved. So the most the 90% conversion and 99% selectivity is achieved on 1 weight% vanadium oxide and down on strontium titaniate, whereas it goes down to 80 and 60, because this decrease in activity is mainly due to change in morphology of the sample. So this is the thing. So sorry, I forgot to tell this. Benzyl alcohol is converting into benzaldehyde. This is the mechanism. So this is if it over oxidizes, it also forms benzoic acid and benzoate. We have also tried on a different benzyl alcohol substrates, and each and every substrate yield desired good yields for desired crops. That I'm not going into details. And we have also tested, we have taken 1 weight% vanadium oxide and strontium oxide and tested for recyclability, and it is observed that we can use maximum for 3 times without loss in activity. After that, you can see loss in activity takes place. This is due to physical loss of the material, but not the leaching. Leaching is different. So here is a physical loss of the material because we have taken only 80 mg. So now the most awaiting field is photovoltaics, even though it is not my field of research. So I want to just brief about the photovoltaic applications of these materials. So this is the material, the perovskite material which we use for photovoltaic cells are the hybrid organic and inorganic metal halide perovskites. So the structure is, so A is the organic part, which is methyl ammonium or a formaldinium, which occupies the vertex of the face-centered cubic lattice. You can see all the blue things, all the organic ions, and the metal, it can be lead or tin, occupies the center of the octahedron, and the anions, which can be chloride, bromide, or a mixture of these things occupies the effects of the octahedron. Okay, this is the structure of metal halide. So what are the characteristics, main characteristic features of these perovskites that makes them, wonderful materials for solar cell? We will see there are four main characteristics makes them. First is these materials possess excellent photoelectric properties. Excellent means they convert light into electricity, and they do have lower exciton binding energies and high optical absorption coefficient. Okay, so lower exciton binding energies means they can form free excitons, which are free electrons and holes. That's what we want, separation. We don't want to we don't want to combine them. Okay, so they do have the good excellent photoelectric properties and low exciton binding energies and high absorption, basically broad absorption. Secondly, perovskite has the light absorbing layer and can absorb solar energy efficiently. So most of the light in the visible region can be absorbed by the perovskites. That is the beauty of these materials. And these materials possess a large dielectric constant, and electrons and holes can be effectively transmitted through them and can be collected. Lastly, electrons and holes can be transmitted simultaneously or separately, and the transmission distance is 100 nanometers or even more, up to 1 micron. So, long transmitted distance. These four characteristic features of these materials make them, promising materials for solar cell applications. So this is the configuration. This is the glass substrate, and this is a fluorine doped titanium oxide, and the fluorine doped tin oxide, not titanium. This is a titanium layer, and perovskite, and this is the organic and indium zirconium oxide. So when this cell exposed to the solar light or sun, so what happens? The electrons and holes are created in the perovskite layer, and later the whole transport material and electron transport material such as TaO2 collected the holes and collected the holes and the electrons. Suppose here ETM, electron transport layer, is a TaO2. So because of difference in the exciton binding energies, they can be separated efficiently by the perovskite layer, and holes collected by the titanium, electrons collected by the titanium layer, and the holes collected by the whole transport material, and these further collected by the electrode material here. So electrons by FTO material and holes by the electrode, and these two electrode materials are connected, and the photocurrent is generated in the outer circuit. So, what are the advantages and disadvantages of perovskite solar cells? One is high carrier mobility, long diffusion distance, long lifetime of the carriers before they recombine, low carrier recombination because they are a long time diffusion and a long lifetime of the carriers. That's the reason a low carrier recombination, and high conversion efficiency, 25% certified by National Renewable Energy Laboratories, Department of Atomic Energy in US. So these are the advantages. But for every system, there are advantages and disadvantages. Not every single material is highly advantageous. Okay, even though there are a lot of advantages are there, disadvantages about these materials are the stability. So this conversion efficiency is not stable. With the time, it is going down. That's where the research R&D comes in, plays a significant role about these materials. And another thing is the lead. So far, lead is the most active component here. So replacement of lead with environmentally friendly elements in the perovskite material will protect the environment also. So basically, I just included the brief discussion on solar cell because I'm not working on that. Conclusions. So what I have done so far. So regarding perovskite research, I have developed new methods to synthesize them at low temperature. Uh, okay, so that Perovskite means what all the time perovskites. So a lot of literature available on them studying electrical, optical, and magnetic properties of this material. Catalysis part is underexplored. So where I really take up that as a challenge and I worked and I discovered new methods for the synthesis of porous nano perovskite materials and. Invention of new materials such as supported perovskites, right? And you won't get, you type supported perovskites, nothing, just except my paper published in chemistry selector will come up in the search. And, all the materials that I prepared, studied using modern characterization, explored these catalysts for the first time for liquid phase organic transformations. And in every study I did, I always try to develop some structure activity relationships. What is the structure and how does this impact the catalytic activity of this material? So always I improve the or develop a structure activity relationship for whatever the materials I studied and identified new catalytic process for the synthesis of hydroxybenzene and aniline and explored as catalyst in the water remediation, which is the degradation of nitrobenzene we have done, and almost all the things which I just presented for photocatalytic degradation, kinetic and mechanic studies, and two papers are under review now, where I use it for the perovskites for the degradation of chloroorganics, and another important application is I disperse this perovskite nanomaterial in the polymer and I use it that one for the cleaning of oil in water. So hopefully those results will be published and so with this I really thank Professor Shukla to give opportunity to interact with all you. Any questions and I can take. I think I have taken long time since.
It's okay, ma'am. No problem. Thank you
So,
so much.
thank you very much, madam. And before I go for the vote of thanks, our colleague, I will like to interact you for 2 minutes.
Sure,
Uh,
it's my pleasure.
yes, yes, and you have done very extensive work and studies on perovskites, particularly strontium titanate and
Yes,
strontium ferrites, and
yeah,
lot of it, you have covered complete spectrum of studies, starting from the basic raw material to synthesis by two methods, and very later on extended to
yes,
application in reduction process or photocatalytic oxidation and so on. Wonderful work you have done and lot of data you have generated. My congratulations to you for extending in this
thank
field.
you,
That is one thing. I have
thank you.
a very small one question I wanted to clarify from the expert like you. Uh,
Yeah,
these
sir,
uh,
please tell me.
these materials are extremely important, in my opinion, from the futuristic point of view. And you might have noticed also they are very strong reduction catalyst. But I don't know. You have chosen nitrobenzene particularly for reduction process and used your strontium titanate and strontium ferrites, and you
Yes,
have seen the effect. And I think you have compared with the metal halide type of perovskites catalytic activity also. Now here I wanted maybe to suggest that you can extend your this catalytic reduction activity of your these two perovskites, say for the reduction of oxygen itself. I'm talking about fuel cell application point of view. When you are using hydrogen oxygen fuel cell, so one of the most there are two important reaction: hydrogen oxidation and oxidation reduction at
yes,
cathode. And
yeah,
they are using nowadays in the platinum and palladium based catalyst for the reduction of oxygen, which are extremely costly, and that is why fuel cells are not so popular, and because high cost involved in the noble metals to use
yes,
now.
yes, yes.
your catalysts have such a great potential to reduce the, I'm sure they will be effective in oxygen reduction also, and you have used the doping with chromium as well as vanadium pentoxide.
Yeah.
So, I wish you can extend your study on very simplest possible reaction of the nature is oxidation reduction, correct? No, and that will,
Yes, sir.
if you can, if you have some experience in this field, you can share with me and with our audience, or you
So,
can extend your study at a later date through your students. It can be a wonderful
uh,
field. In case it is successful, you can remove all the novel catalyst and put your this strontium titanate based or ferrite based simple and low cost catalyst,
yes, yes.
and doped with maybe
Uh,
transition metals like chromium or nickel or whatever effective manganese, or maybe I don't know. There is a
Sir,
ocean of things which can
actually,
be done.
actually, in fuel cells, they used as cathode, cathode and anode material. If you see some of the applications, hydrogen, putting there are applications. If you can just type of fuel cell kind of thing, but the results are not promising. It's
Okay.
somewhat, and that's the reason. Yeah, but as you suggested, it is like now we take up that one, we investigate further into that one, and to improve their performance in the fuel cells. Definitely, I will take your suggestion and definitely look into this one. Hopefully, maybe in future, I could able to explore in that line. But applications are there, but
Yeah,
not
yeah.
but not very promising. But not very
Okay,
promising.
okay.
Yeah, applications
Maybe
are
with some
there.
dopings, you can further increase the catalytic effectiveness.
Yes, yes,
And
yes,
if you
yes,
can
yes,
click through it, then I am sure this is going to be very, very valuable work, because
yes,
the bottleneck in the fuel cell is the catalyst, electron
yes,
catalyst.
yes, yes. And also cobalt-based perovskite considered as replacement for platinum catalyst in
Yes, yes,
catalytic converters in
exactly,
diesel vehicles.
exactly.
So that is also something. Actually, my DST inspired project is on that one. Finding applications for auto exhaust catalysis using perovskites. But in IAC the facilities are not available, so I need to come up. DST told me that you need to stick to perovskites and do something new. So if you
Yes,
don't have the facilities to study auto exhaust catalysis and all, then after thorough research I came up where these materials are underexplored. I have chosen this liquid phase organic transformations, and they came up with normally if you see hydrogenation, we should use hydrogen at elevated pressures. But
yeah.
here I came up with just you can conduct this one at lower temperatures using hydrogen
Okay, yes,
hydrate
yes.
and
Correct,
isopropanol.
correct. I
That
have
is the
noticed. Yes.
yes, sir. That is the beauty of the catalyst. Here, that is catalytic transfer hydrogenation. So your
Yeah.
reducing agent is splits into two, and the hydrogen that is produced from decomposition is using as the hydrogenating agent. That is the beauty, and if you see, if you type it, only my publications will come. So
Okay.
that's the thing. Somewhere, what I can do in the facilities given or provided by IAC. So I have done that one. Okay, so gaseous hydrogen elevated pressures is completely replaced with the reducing agents, so that you can
Yes.
conduct the same hydrogenation reactions at low temperatures just by using the reducing agents such as hydrogen hydrate and isopropanol. So the name, another name given is catalytic transfer hydrogenation or catalytic reduction. So that is something is new actually. That's the thing, but it is a wonderful idea, as you said. Definitely, now we have facilities available also in Githam. So, electrochemistry laboratory is there. So, I want to explore your suggestion further.
Okay, thank you very much. And one small question I have, because
Yes,
these
sir.
perovskites are also available as mineral from the rocks, maybe
Mm-hmm.
from the earth crust, or maybe from the nature, they are available.
Mm.
Have they been, because they may be contaminated with other impurities in
Yes.
between the layers. So,
Yeah.
but whether they have been tried out as a catalytic material or certain other application and compared with the synthesized ones, the pure materials, pure perovskites. Is there any data available? Is it
Actually,
worth
sir,
trying?
so geolites are available. Natural geolites are available in the
Yes,
market,
yes.
for purchase, but not the perovskites. In India,
Okay.
it is. So I tried actually. I tried. So
Okay,
normally, if
yeah.
you see geolite catalysis, they will buy from the market, and we have, but I don't know. Only India it is like that, or somewhere else also. Here it is. Market is not there for
Okay, okay, okay.
natural perovskites.
Yes,
So
yes, yes.
definitely we have to synthesize them. And as you can see, I have used two methods, conventional and microwave. Conventional contains impurities. That affects the activity actually.
Correct,
That
correct,
affects the
correct.
catalytic activity.
Yes,
Suppose if
yes,
you
yes.
use natural thing, it
Yeah,
contains lot of impurities.
right,
Definitely, you have to clean that up, or you have to treat them, to make it pure
right.
phases.
Correct,
So or
correct.
otherwise, it is catalytic activity is very sensitive to the impurities present in our
Yeah,
material.
yeah. So thank you
Yeah.
very much for giving the clarity on the subject and a lot
Thank
of
you, sir.
learning material for all of us. And
Thank you,
I'm
sir.
grateful to you for sparing so much time for us and for not only for our college, for the entire, you can say the scientific community, because this is on YouTube. And
Okay.
very many people must be going through it, and it will be available for in the next 1 or 2 or 3 or maybe more weeks on YouTube,
Okay.
so that
Okay.
it is available in public domain and they can learn out of it. There is a plenty of
Okay.
knowledge available, and I'm so grateful that you agreed immediately,
Thank
and
you.
we managed to do it
So my
despite
pleasure.
some interruptions. So it's all God's blessing that we are seeing each other after such a long time, maybe around 10 years. Yes,
We
more
are
than 10 years.
becoming old. We are becoming old, but not you.
Okay. So thank you very much
Your days,
for
you,
you, not only Dr. Srilakshmi, also the management of Geetam University, who permitted you to present such a beautiful and wonderful
correct,
research work.
correct.
And
Yes.
now I will, of course, my grateful thanks to you. And now I am switching over to my colleague, Dr. Dorai Swami. He is professor and HOD of mathematics department. He would like to say a few words on word of thanks. And thanks to
Okay.
you and your institution who have put so many efforts in order to make this event successful. So I will switch over to Dr. Dorai Swami, sir, for word of thanks, sir.
Yes, sir. Now I request Dr. Doreswamy sir to give a vote of thanks. Over to you, sir.
Okay, good evening, all. Thank you is such a prayer that cannot be seen or touched. It must be felt by heart. I feel honored and privileged to get the opportunity to propose a vote of thanks on this occasion. I would like to thank today's chief guest, Dr. Srilakshmi, Department of Chemistry, Geetam University, Bangalore, for her valuable speech about advanced materials. I, on behalf of the organizing committee, convey sincere regards and hearty thanks to our honorable CEOs, Pramod Goda sir and Rajiv Goda sir. I am also thankful to our director, Dr. Shankapal sir. They supposed in all possible manner to organize this webinar. My sincere thanks to our principal, Dr. Satish sir, for his help and support at various stages. I would like to thank our first year coordinator, Dr. Maruti sir, who always stand by us and motivate us. I would like to thank our beloved head of the Department of Chemistry, Dr. Ashok Kumar Shukla sir, for his constant help and guidance that radiated a source of energy within us. We will ever remain grateful to you, sir. I am very much thankful to all the department HODs, professors, teaching and non-teaching faculties for grand success of this seminar because of our students. Thanks to all of you for making this event successful. Have a wonderful staying at East Point Group of Institutions. Thank you. Thank you once again.
Thank you, sir.
Thank you, sir. Thank you, ma'am.
So, thank you, madam, very much. And with that, we are concluding our today's event and program. And we are going to remain very grateful to you and your efforts which you have put forth in making the preparation for this webinar. I'm sure you might have devoted so many days in collecting the data and organizing it so that you can present it smoothly
No,
today.
actually, whatever I presented, everything published.
No, that
Everything
is
is
how it should
published.
be.
Yeah,
Presentation should
everything
be
is
after
published.
publication. Yes, yes, yes,
Yes.
yes. So that no risk is involved and your data is safe. So thank you very much. My grateful thanks extend to your management and Geetham University authorities who have given
Yes.
you permission to spend so much time for us.
Yes.
God
Yes.
bless you all. And I
Thank
always
you.
wish that a Geetham University, along with our institution, should grow leaps and bound in future for the service of mankind, of our nation, and of the mankind throughout the world. Because this service, science service is supreme. It is for all the mankind, for the betterment of mankind.
So actually, last I would like to invite you all to our campus whenever you are coming this side, or if you need any assistance in terms of internship for our students. We do have research labs, and very soon we are developing central research facility
Yes,
here. For that, we are investing. Our management is very kind enough to invest into it because our young and dynamic president, Mr. Bharat Garu, want to convert this institute into research and academic based, both more of research side. That's the reason
yes,
we are in the process of developing central research facility. We do have basic labs, as I showed you in my presentation, but what is lacking is equipment which we can use around within the institution for characterization. Now we are collaborating with IAC, and MOUs with IACT and all. Maybe in 6 months down the line, we are placing orders now for from small to medium equipment like XRD, FTI, RGC, mass and all. So I was working on it, actually involved in the layout plan of the Central Research Laboratory and all. Hopefully, in 6 months' time, we are having full-fledged Central Research facilities, and we can expect very good publications and very good research, from Geetham. In case if you want to collaborate with us, welcome. And if you need any
yeah.
internships for your students also, you are always welcome to Geetham University, and you are coming this side, and you are invited to come and visit us to see our labs and all. Thank you so much for giving this
So thank
wonderful
you very much, and
opportunity. Thank
surely we
you.
are going to consider the proposal, and we are going to make use of the facilities you have generated at your
Yes.
institution, at your department, these research
Yes.
facilities. And I am happy that they are available in Bangalore in case our
Yes, of
allied groups
course.
who are working in this field and students project
Yeah.
work, they can approach you and
Yes.
your facility and take advantage of
Yes.
doing the certain studies in your labs.
Yes.
Okay,
Yes,
thank
sir.
you very much
Surely.
for madam proposal, and my grateful thanks to you and your management. And I'm very, very grateful that you have spent so much time in preparation of this, and somehow we managed to conduct this webinar, which was awaited for more than a month or so. But
Yes, because normally I was so busy. So this
I
time,
know, not only your side, this side also same situation. Only last Saturday I
so,
completed the VTU exams of practicals and all.
okay.
And now
So
new session already started.
yes, yes.
So thank you very
So
much. God bless
thank you,
you.
sir. It's my
Thank you.
pleasure all the time. So
Yes,
take leave,
thank you.
sir. Thank you.
So we'll conclude with God's blessings.
Yes, sir.
Okay, thank you, Gayatri madam.